Alright, I'll give it a shot. Forget the ego and the id. I'll start with the fundamentals. The body has nerves to sense its environment and uses muscles to respond to that environment. Nerves can be connected directly to the muscles, allowing them to respond quickly. This explains muscle memory and why the heart can beat for a short time after it has been removed from the body. For more complex operations, we must dive in deeper. Nerves can be seen as electrical wires that carry a signal. This signal will be the voltage in the nerve. Rather than use the voltage levels, a letter can be assigned to a specific voltage. When the signal in several nerves is read, these voltage levels will form words. On the other side, the muscles will be controlled by wires that carry a voltage. Once again, the voltage can be represented by a character. The signal in several of these wires can be represented by a word. For more complex operations, there must be a switching system to allow different muscle movements that change as the nerve values change. To handle inputs, a pattern generator will scan a series of nerves and then determine their voltage values to create a word that can be used by the muscles. The response controller will take a word representing voltage values and send these values to the appropriate muscles. These switches still do not allow the muscles to respond to different inputs. Other elements are required for that. What is needed is a method of holding a series of inputs and matching them to the appropriate outputs. The simplest implementation of this is to use a table that holds nerve patterns matched to a response for the muscles. This can be a simple table with only 3 columns. The first column holds input patterns like those sent from the pattern generator. The next is the row number of each table entry. The final column holds responses to be sent to the response controller. The pattern matcher scans the table for the pattern that matches the input word and sends the appropriate response to the response controller. The body will react with the designated response whenever the pattern is met. If I were to pop a balloon in the face of a baby, the baby would associate balloons with an explosive, dangerous event and match it with the fight-flight response. Later in life, whenever a balloon is seen, the fight-flight response would be triggered. This is known as a phobia, which is one of the mental afflictions. To see how this works, I'll start with a simple example to understand the process, sending through commands for the eyelids only. When the eyelids are closed, the command is sent to open the eyes. Once this is sent through and processed, the command to close the eyes is given. In reality, every nerve in the body would be providing information to move every muscle. This results in more patterns being sent through, and this illustrates a serious design flaw. It will take a long time to locate a match. A smaller table will take less time to find matches, but it will be less capable than a larger table. To make the table as small as possible, the entries will be devoted to those required to survive and reproduce. This leads to the obvious question: what are these? The obvious answer is the ones that have already been used. To locate these, there must be a period of learning in the animal's life when new entries are placed on the table. During this time, the table will require extra spaces to allow new matches to be inserted. Eventually, there will come a time when the animal will know all it needs to survive. At this point, it is advantageous to remove the spaces and close off the table to speed up reflexes. The table would hold the entire set of muscle movements for all nerve inputs. This set could be seen as the personality. If the table were to fragment into different segments, each segment would become its own personality. The individual would appear to have multiple personalities. Hey, that's another mental affliction. Rather than make the whole system wait while patterns are located, a pattern buffer will be added. This is a storage area to hold patterns while the system searches for new matches. The pattern buffer will not solve the problem of locating matches. It will merely delay the onset of the problem. A better solution would be to try to anticipate the next pattern to arrive. If this were possible, the table could be moved to the appropriate position to allow the match to be located quickly. To do this, another table must be added. I'll call this the anticipation table. This table would require 7 columns. The first column holds the row number of the table. To avoid confusion with 2 row numbers, the anticipation table's row number will be called the reference number. The next column holds the next expected pattern. This is followed by the row number of the pattern response table, where the next expected pattern can be found. The following column will hold the next reference number in the series. This is the row number of the next pattern that is expected to arrive. The next 2 columns hold the confidence level and search width. The search width holds the number of rows above and below the expected row number over which the pattern response table must search. If the system is confident that the next expected pattern will be at the row number, the search width can be very small. When a correct match is located, the confidence level will rise by a value equal to the weighting. If the match is not found, the weighting value will be subtracted from the confidence level. For now, the weighting value will be equal to 1. The search width will be equal to the whole part of the table size divided by the confidence level plus 1. For example, if the pattern response table has 40 rows and the confidence level is equal to 5, then the search width will be equal to 40 divided by 6, or 6 2/3. Since the model cannot search 2/3 of a row, this value will always be rounded down to the whole number. In this case, it will be 6. The final column will be explained later. While this is a nice looking table with its matching color scheme and everything, how can the system ever hope to know what the next pattern will be? Maybe I should include a crystal ball in the design. Of course, I could always solve the problem in a religious manner. If I wanted to be a prophet and impress the religious community, I would get a history book, rewrite it in quatrains, and tell everyone it is the future. Soon they would be worshiping at my feet. It is a simple fact that one can predict the future by examining the past. Many of the bodily functions are cyclical in nature, like blinking and heartbeats. The patterns repeat endlessly in a predictable fashion, but these patterns are intermingled in a random assortment that makes prediction impossible, unless they could be separated into individual threads. And separating them is easy if I add a thread controller. The thread controller would examine each input pattern to see if it matches the one it is waiting for. If they match, it will add the row number and search width to the pattern and send this information to the next item. This would have to be a null adder, which will add null, a software term for empty, in place of the row number and search width if none of the thread controllers found a match. In the actual brain, there would be hundreds of thread controllers in operation to handle each thread of patterns coming in. For simplicity, I'll leave it at 3 here. But this final one will have to be devoted to the special case of locating first-time matches. It will work by taking a pattern and then waiting for the pattern to reappear. Since it might grab a pattern that might not reappear for a long time, the thread controller will have a timer that will select a new pattern when the timer reaches 0. But this will only work if the pattern threads are already deinterleaved. And how can I do that? Actually, that will be rather simple. I just have to stop using the anticipation table for a while. Hey, my model needs to go to sleep.